Welcome back to the part 2 of cold storage experiment, that is practical number 3. In this part, we are going to discuss development of process and instrumentation diagram for cold storage plant. In part 1, we have discussed how to determine the refrigeration load of cold storage. We have discussed one sample case study of onion uh, product, and based on that particular sample case study, the work is allocated to storing different products for A, B, and C division. Considering that the plant which is already installed for onion, so that plant which is already installed, that we are going to discuss here. Basically, the content of this experiment or this particular part, the problem statement will be different. So first of all, we'll discuss the problem statement and what are the design criteria for selection of various equipments of the refrigeration system for cold storage. Then refrigeration system selection. There are two major parts of refrigeration system selection: refrigerant selection as well as refrigerant plant equipment selection. And finally, the conclusion part. So the problem statement in this particular part, major problem statement is selection of process equipment. That is the main system is refrigeration system, vapor compression system. So selection of various equipments of refrigeration system and development of process layout means arrangement of these equipments in the stipulated in the given area or in the cold storage, that is process layout of refrigeration system for onion cold storage. So already this plant we are going to develop for onion cold storage. So this particular part you have to copy as it is given. So there is no extra work is there. Only you need to understand the entire design process or the selection process of various equipments. This is problem statement. Then the design criteria for selection of equipments. Well-designed refrigeration system for preservation of perishable products should have all the components properly sized with adequate safety margin over the calculated refrigeration load. So in earlier part, we have calculated refrigeration load around 500 TR, and now we have to design the system to meet that particular load. So the proper design is essential for energy efficiency as well as for safety considerations. It is equally necessary to ensure a proper balance between the capacity of compressor and evaporator at the desired temperature difference, that is TD, between refrigerant temperature in the coil and the air temperature in the cold room, depending on the nature of the stored product. Means already the product is decided, onion we have to design, so the product storage temperature on to us. Based on that, we have to decide the evaporating temperature and condensing temperature. So it is very much essential that whatever the evaporators selected, so the capacity of the compressor selected or the cooling capacity of the compressor selected must meet the evaporator coil capacity. Consequently, the condensers must meet whatever the capacity of the evaporator. It must meet that condensation capacities, and followed by the cooling tower. So there should be a proper balance between these equipments. So that we have to also ensure. Then another important criteria from the point of view of the product safety and flexibility for load management, particularly for large storage, is that the total refrigeration load be divided equally among two or more compressor units and evaporators to avoid product spoilage in the event of electromechanical failures and permit switch off one or more units during low load situations for energy saving. So this is very essential criteria for selection of equipment or designing of refrigeration system, because especially for the large installations, the standby units are must. So for meeting a particular capacity, only if you're choosing only one particular unit, and in case of any failure, the entire plant will be shut off. So standby unit is essential. At the same time, for meeting the low capacity, means low demand. If suppose the storage is low, so it should meet that requirement. So entire plant, instead of running entire plant, if suppose only there is a 25% storage, so only 25% system should be working. So the judicious selection of equipments to meet the low load conditions as well. So this is another important criteria. And yet another important consideration is ensuring adequate air quality and airflow as necessary for maintaining the desired relative humidity conditions. Therefore, the fans of evaporator need to be sized to circulate the required air quality uniformly through the stacks in the entire volume of the storage space. So uniform distribution of the air is most essential criteria. That's why if we choose more than one evaporators, and if the evaporators are placed at the different locations, uh, then it ensures that there should be uniform distribution of air movement. So it should goes to all the stacks and provide the required cooling. So these are some important design criteria of the cold storage. So one must ensure this design criteria while designing the system. Now, refrigeration system selection mainly divided into two. For selection of refrigeration system, various options are available. Options available are considered. The options available include two major selection to be made: that refrigerant selection and the equipment selection. So these are the two major selection categories in the refrigeration system, because first important step, that is we have to select the refrigerant first, and based on the selected refrigerant we have to select the component, or we have to design a refrigeration system. So refrigerant selection done for the refrigeration plant depends on various factors. There are various factors associated with the refrigeration plant refrigerant selection. This includes environmental impact, means the refrigerant must be environment friendly as per the Montreal protocols, policies or environment policies. We have to follow that policy. We should not violate this policy. So environmental impact, or environmentally that refrigerant must be acceptable. So R12 cannot be used nowadays. That, or whatever the what are the refrigerants containing chlorine components are not allowed. So environment consideration is the major considerations, that is mandatory thing. Then the availability of the refrigerant, then the heat transfer characteristics, effect on storage products, stored products. So it should not, in case of leak, that refrigerant should not spoil the product. That consideration is also there. Then what is the refrigerant effect? So ammonia is having a largest refrigerant effect per kg, so it requires less amount of mass and consequently less power consumption is required. So such that the refrigerant effect, so that means the latent heat of the refrigerant is also important. The class of refrigerant, various classes are there, that is halocarbon, hydrocarbons, natural refrigerants. So these classes are also need to be considered. Then discharge temperature and the cost. Adiabatic discharge temperature, because it leads to decompose the refrigerant as well. So adiabatic discharge temperature is also, and last but not least, because for large installations, the cost of the refrigerant also matters, because for example, for every TR 1 kg is required. So for 4,000 TR, the 4,000 gas is required. So especially if the capacity exceeds 1,000 TR, the quantity of the cost of the refrigerant plays an important role as well. A small system, it doesn't matter much, but for large system, the cost it matters a lot. The selection criteria are the refrigerant's environmental impact, its physical and thermal properties, and availability and cost. So based on these selection criteria, especially for cold storage, the three refrigerants shortlisted to meet the closest criteria which are required for the cold storage, that is ammonia is number one, R404 is number two, and R22. So these three refrigerants are shortlisted based on the cold storage applications, and There are few more refrigerants are there, but these are the most suitable refrigerants for cold storage. But out of these three, now we have to select any one. So for ammonia, if we discuss, ammonia being the most efficient natural refrigerant, as it is a natural refrigerant means it is environment friendly, and was obviously the first choice for most of the cold storage applications. But after detailed consideration, it was rejected on the following grounds. So ammonia is rejected in this particular case. So why? We have to justify our rejection as well. So the refrigerant effect affects the quality of food in case of leak. Most of the cold storage applications, ammonia is preferred refrigerant. But if the cold storage, if the stored product is a packaged food, if it is a packaged food, then it is ammonia is recommended. So for example, milk storage, where the milk bags are stored. So even in case of leakage of the ammonia, it should not spoil the milk. But in this particular case, as vegetables, fruits, these are the unpacked products. So in that case, in case of leak, ammonia spoil these products. So on that is the first criteria, the ammonia is rejected. Uh, semi-hermetic compressors are not available as on date for ammonia. Ammonia has certain restrictions. Ammonia works well only with the reciprocating compressor. But as far as the current advanced technology is concerned, the reciprocating compressors are now replaced by screw compressors, scroll compressors, and these are available in semi-hermetic formats. So ammonia is not still compatible with the semi-hermetical compressor structures. To make the plant totally safe in case of accidental ammonia leaks would mean high initial costs due to safety measures required as per the standards. So ammonia being a flammable gas, so in case of leak, uh, there is a possibility of some issues. So high safety considerations required. If we select ammonia, we need to follow these safety standards. That is the one reason we are eliminating ammonia as the refrigerant. So these are the three main reasons why ammonia is rejected as a refrigerant. In spite of its good qualities like latency is good, low mass flow rate is required, ammonia is compatible with flooded refrigerants, its cost is also low, thermal properties are good. But in spite of that, this refrigerant is rejected because of the safety considerations, because of its spoilage, and the third one, the ammonia uh, is not still compatible with the advanced refrigerants or new refrigerants. That's why it is rejected. 404A is normally the preferred refrigerant for low temperature applications. Uh, this is the medium temperature application. So 404A is especially suitable for a very low temperature, means below minus 20 degrees Celsius because of its lower boiling point. It's a blend of HFCs. At higher temperature, R22 has better efficiency than compared to R404A. Comparatively, it gives better theoretical COP because of low compressor pressure. And R404A refrigerant is also non-azeotropic mixture. In case of leaks, top-up is not possible. That is a problem with non-azeotropic mixture. If in case of leak, the composition disturbs, and in case of top-up also, the correct composition, it is very difficult to recharge. So that's why the entire characteristic of the refrigerant may change. So these refrigerants, especially non-azeotropic mixtures, they are not at all suitable. Or in case of leak, the entire refrigerant to be replaced with the new one. The top-up is not permissible. So these are some causes where the 404 is also uh, rejected. And the last one, it mainly requires POE lubricants to be used, which are highly hygroscopic compared to mineral oils. It has affinity to absorb moisture. This require highly specialized skills in the designing of piping and installation, as well as for evacuation dehydration techniques. So that is the problem associated with hydrocarbon refrigerant, because hydrocarbon refrigerant POE oil and is highly hygroscopic. So high level evacuation is required. So at the time of charging is slightly complicated process. That these are the four drawbacks of the R404A. And in view of these considerations, 404A was not considered for the plant design. Then R22 refrigerant, although it has some environmental impact, means its global warming potential is very high due to its small ODP and comparatively large GWP. It is still allowed till the year 2020, but its use is permissible till 2040. So R22 it's shortlisted. Another reason that the skilled manpower for installation maintenance is readily available for R22 refrigerants, and there is a greater confidence in operating R22 plants compared to R40A, 404A installations. So most of the consultants still rely on R22 because of its um, uh, um, greater expertise available across the globe. But the R22 refrigerant is also more efficient in temperature range because this is a medium temperature application. So for these applications, R22 is suitable at which plant is supposed to operate. In view of these considerations, R22 was selected as the final choice. So these are the ways of selection of, this is just a sample case, how to select. So there are 20 desirable properties of the ideal refrigerants, but all 20 but a single refrigerant should not possess all 20 properties. So the properties which are mostly suited the given applications are first need to be listed out, and then the best possible refrigerant to meet these properties are selected or is selected. So this is generally a policy of selection of a refrigerant. Uh, uh, Most of the applications, some refrigerants are dominant, like ammonia is dominant in large refrigeration applications, even in cold storage also, but not preferred for storing the unpacked products. Then the equipment selection is based on the keeping in mind the flexibility, then reliability, available space, and operating and the capital cost. So these are the factors need to be considered while selection of the equipments, that is refrigeration equipments. Flexibility in the sense there should be a proper uh, capacity modulation uh, need to be incorporated. And then it should be reliable because the reliability is the major concern, because in case of breakdown there is a possibility of heavy loss, both as well as in case of product which is stored, if it spoils because of the breakdown, then it costs heavily for the um, plant owner. The available space that depending upon the size of that is not the major criteria in cold storage, but cost is also the major criteria. Uh, in equipment selection, it mainly includes selection of the following equipments: that evaporator, compressor, condenser, expansion valves, and cooling tower. So all these components are selected because most of the cold storages, most of the cases evaporator need to be designed. But in cold storage application, most of the components are selected and they installed uh, in the plant. That's it. Only the assembly part is only done. So these are the components need to be selected. These are the major components. Besides this, there are some control systems are also there. But these are the major components we are going to select in this particular session, this experiment. Evaporator selection, evaporator mainly in the previous part we have discussed, there are 6 chambers. and the total load is 8400 metric ton onion to be stored. Obviously, this metric ton is equally distributed in all chambers. So the storage capacity of each chamber is 1400 metric ton. So this is actually a storage that is holding capacity of the holding requirement of the cold storage. But there is some pre-cooling requirement is also the pre-cooling capacity of the entire plant, or the requirement is 1400 metric ton. But the problem is that the pre-cooling of 1400 metric onion in one chamber is not possible due to huge refrigeration load. So the refrigeration load estimated to be around 190 TR. So 190 TR in one particular room accommodation is not that much possible, because the size of refrigerant or size of evaporators are concerned, it is very difficult to accommodate all. Thus, it is divided into 6 chambers. So 6 chambers we can divide. So ultimately 1400 means in 4 chambers, 200 each, it becomes 800, and in 2 chambers, the 300 each, so it becomes 600. So 800 plus 600, that is 1400 metric ton, that is pre-cooled. The other handles 200 metric ton for free cooling, and so this is a contribution. So 300 in center, because the central chambers have less. Why the central chambers are selected in this case? Because central chambers have less transmission load, because it's 2 phases. Only one phase is exposed to solar radiation. Obviously, the major transmission load bared by the chambers, which there are almost 2 sides exposed. So these chambers generally experiences more solar radiation. So that's why the central chambers are selected for storing more quantity of pre-cooling. So this is actually the load distribution, that is the storage capacities. Means first of all we have to distribute the onion, and now we have to calculate the refrigeration capacity of each chamber. Now chamber 1, 3, 4, 6, they have a identical load, the same refrigeration load, and chamber 2 and 5 are the same load. So the refrigeration capacity or load of chamber 1, 3, 4, 6 are same, and the refrigeration capacity of chamber 2 and 5 are same. Now, first of all, we'll discuss chamber 1, 3, 4, and 6. So for example, pre-cooling load, that MCP delta T, if we calculate, now here the pre-cooling load is already, we have decided that is 200 metric ton. Specific heat is known to us, incoming, and so the pre-cooling load is around 27.3 TR. So these are the pre-cooling load, we can say. So 27.3 TR in each chamber. So chamber 1, 3, 4, and 6, 27.3 TR. So that is actually a refrigeration load of that particular chamber only for pre-cooling purpose. So pre-cooling is at the entry, because this is our passage. So loading and unloading, the passage is provided. So immediately at the entry, pre-cooling space is provided. So after pre-cooling, it only shifting towards the wall side, and the new pre-cooling can be loaded. So for convenience, only at the entry, the pre-cooling space is provided, and at the wall side, the storage space is provided. Now, the holding capacity, that is respiration heat load, we can calculate, that is for 1400 metric ton. So it comes around 140 kilowatt or 39.80 TR. And the other shared load, because other lighting load, occupation load, transmission load, so it is equally shared in each chamber, and that comes around 48.28 kilowatt, that is 13. So this becomes 53.52. So that 53.52, that is a load which is a storage load, along with the other supporting other shared load of the chamber. So this is a total capacity. If we see the total capacity is around 80 TR of one particular chamber. So that is 80 TR is the total storage capacity of a chamber 1346. But out of that, 27 TR is for pre-cooling, which is not required continuously, only during a fresh mal, during a fresh storage, it is required to bring the temperature to the storage temperature. Uh, and this is our continuous load, it's 53.52. So it is always recommended to have two different systems to bear a regular load as well as the pre-cooling load. So this is for 1346. So the total load of is the 80.81 TR. So this is for these chambers. So remaining two chambers, that is chamber number 2 and 5, the pre-cooling load comes around because their more 300 metric ton is stored, so it is comes around 41 TR, and the respiration load is which is same because 1400 metric ton is the load, and considering other, so it becomes 94. So 15 TR more load is there for chamber number 2 and 5. So 41 TR, closely 40.94 TR is the pre-cooling, and 53.52 is same for chamber 2 and 5. So this is a refrigeration load for chamber 2 and 5. So before selection of evaporators, so first we have calculated the refrigeration load of each chamber. We already calculated the total refrigeration load, but here that distribution we have calculated chamber wise. So this is a distribution of refrigeration load chamber wise. And now we have to select the refrigerant or select the evaporator to meet this distribution. Now, as per the design criteria, the two, two evaporators required to meet the refrigeration load means instead of one refrigeration. So to meet this load, that is 50 TR, instead of choosing a one evaporator of 50 TR, choose two evaporators of 25, 26 TR each. So here roughly about 27 TR capacity capacity evaporator we need to select, and here around 15 TR each evaporator. So it should be slightly greater than the refrigeration load. So by taking some margin. So this is good. That means, for example, so that is 26 TR two evaporators for meeting regular load, and almost 15 TR of two evaporators meeting pre-cooling load. So there are four evaporators need to be installed in chambers. That is chamber 1, 3, 4, 6 of uh, 27 TR and 16 TR, 15 TR respectively. Here slightly more requirement is more. So 20 TR, and here again almost 26 TR, 26, 27 TR. But instead of that, if we select 27 TR for this also, so slightly over capacity, but instead of selecting the different, only two types of units we will select here. So that is 27 TR and 15 TR or 16 TR. Means two types of evaporators to meet the entire load. And now we'll select the for rating and selection of evaporators. The basic ratings for means while selection of evaporator, the information required, because most of the evaporators, the catalogs are in still the British thermal units, that and that is not in SI units. SI units are generally for only the education purpose, but most of the commercial catalogs, they are not available in SI units. So for convenience, sometimes the ratings are given in degree Fahrenheit, that is 10 degree Fahrenheit and 15 degree Fahrenheit TD. So various TDs are available. So because now evaporators are essentially for cold storage evaporators, they are essentially fin tube type forced cooled evaporators. So following are the design conditions used during selection. So capacity, all as we have already decided, 27 and 50 TR capacity evaporator, close to that. We need to select for adequate air quantity and air flow as necessary for maintaining the desired RH value. So instead of selecting only one evaporator for one capacity, the two evaporators, two or more evaporators need to be selected as per the design criteria. In this case, we are going to select two. The total load is shared in 4 units in such a way that the 2 units are used for pre-cooling purpose and the two are for other loads. The design TD in this case, the storage temperature is 2 degrees Celsius. Generally, the evaporating temperature in the multiple of 5. So 0 is not because it is very low TD. So instead of 0, uh, we can select -5. So -5 is the evaporating temperature. So -5, -10, -15. Because if you see the catalogs of the compressors and the evaporators, they are in the multiple of 5 degrees Celsius. Then 0, 5, 10, 15 like that. So here 2 -5, the 7 degrees Celsius is design TD. And if we convert into Fahrenheit, it is 12.6 degree Fahrenheit. So the evaporating temperature is taken as -5 degrees Celsius for selecting the compressor as well. So evaporating temperature is below 32 degrees Celsius. So there are some in the table, the evaporators mainly capacities are given on the systems above 0 degrees Celsius and below 0 degrees Celsius. So this is actually the model generally used for cold storage with forced cool because fin tube evaporators, and they're generally installed at the roof or on the wall, maybe because of the the floor space is utilized for the storage. So mainly it is installed on the wall or roof. So this is the model, and this model is selected from the table. Such kind of catalogs are available with the manufacturers of the evaporator. So this is a sample catalog. So the model numbers are given. Then what is the CFM? Then what is the face area? Then what are the rows there? So as far as possible, low rows are recommended to have a low fan pressure. So 4, 6, 8 rows are given. Then these are the two categories: above 32 degree Fahrenheit evaporating temperature or below 32 degree Fahrenheit evaporating temperature. And also fin per inches. So 3 fins per inches, 4 fin per inches. These are the requirements. The total surface area is also given. Then centrifugal blower size and other details are given, and what should be the gallon per minute for water in case. It is also recommended here if the chill water is used there. So based on that, it is for pre-cooling mainly the recommended capacity is actually the 4 fin per inch is recommended because their fast cooling is required. So contact factor should be high, means bypass factor should be low. So the fast cooling generally uh, more fins are preferred, and for regular cooling where the delta T is very low, in that case the fins per inch may be minimized. Because increasing number of fins causes more pressure drop for the fan, so it causes more power consumption of the blower, but it gives fast cooling as well. So fast coolers are generally preferred for pre-cooling. So for pre-cooling application, we select 4 fin per inch um, mm, the configuration. And the DX type, because this is R22 are mainly suitable for DX type evaporator. Flooded evaporators are especially used for ammonia case, not in hydrocarbon or halocarbon refrigerants, generally DX evaporator. So these two criteria are selected, and below 32 degrees Celsius, because our case it is -5 degrees Celsius. So first of all, we have to decide which column we have to go for. So now for pre-cooling application, so more number of fins per inch to get a fast cooling, as R22DX type is preferred and it is already below 32 categories. So this row we have to select, and in this row our capacity is expected capacity is around 15 TR, and if we see 15 TR, then it comes around 16,000, that is BTU per hour per degree Fahrenheit TD. So first of all, we have to calculate what should be the magnitude required, because TD known to us. So what should be the magnitude required? So around this 16,000 BTU per degree Fahrenheit per TD, it's around that is for the 16 TR. But the next below that it's very low. So this model is selected for the application. So this is selected model. Then for the second case, that is for regular cooling, that is for holding the onion for a longer period. Now here the delta T is very less because already 2 degrees reach. Now we have to maintain that 2 degrees Celsius. So here comparatively less fins can be used with the X-ray. So this column we have to go for. And based on the capacity, we have selected this particular capacity, that is for the below 32 degree Fahrenheit. So this model is selected. So this is a way of selection of model. Now we have a information. So which model to be selected, what should be the capacity of the evaporator based on that, and which column to be selected. So first of all, we have to shortlist this column, and in that column, which particular model meets our requirement, accordingly we have to select. Now here, this 16,000 is our criteria. 16,000 is the requirement, so less than 16,000, 15,000 maybe. But this meets the requirement, and here this 23,500 meets the requirement. So these two models are selected. So other details of these models you can see for it's 16.8 TR, that is model that is selected for pre-cooling application. So its construction is 4 fin per inch. 8 rows are there. Rows are also less because we have to go for rows, lesser rows, because for lower, because 6 rows is not available. But here we will select. If you see here, the 8 rows, that is in between, because 6 the capacity is comparatively less. 4 is capacity is less. So the in between rows. So as low rows are beneficial because more rows gives a better TD as well, but it gives a greater pressure drop as well. So in between the break-even is of 8 rows selected. These are the configurations for model which is selected for pre-cooling applications. So 16, so there are 8 units are selected, and for the second model where the 23,500 BTU per is the capacity, equivalent capacity, that if you convert into TR, that is around 25 TR. So for that is 50 TR. So means 16 TR can be used for pre-cooling, and 16 units. But in that case, one is used for pre-cooling. Is this there are only these four chambers these models are used, and in middle two chambers, I think the same unit can be used here. So the configurations, if you see the to meet the requirement, this requirement, these are the models selected. So 24.7 TR, these are the 16 models. So each chamber for meeting this load, so already 2 units, so 12 units this, and in the middle two also the 4 or 2 units each, so 16 units for model 1, and that is only 8 units of model 2 of 16 TR, which is especially used for pre-cooling of the chamber 1, 3, 4, and 6. Here the load is comparatively high because if we see that is around 24, that is 100 TR load is there. And here if you see the load is around 90 TR. So 10 TR extra, but obviously we can slightly oversized evaporators will do because by controlling the refrigerants we can control the capacity as well. So instead of choosing the multiple models, only 2 models are selected here. So we have slightly compromise here the load. So slightly chamber 2 and 5, the oversized evaporators are selected, but that is not an issue because we can meet the requirement with by controlling the refrigerant flow as well. So this is about the evaporators. Then compressor selection, because the compressor is the largest power consuming device in the cold storage or any large installation. Thus the selection of type of compressor, that is open type, semi-hermetic, screw, or reciprocating, is to be done judiciously. Thus the selection is done and considering the following points: the type of refrigerant, operating conditions, size of the unit, noise level, erection and service access, then energy efficiency and capacity control. So latest models can be selected here. So to select a compressor for given application, the following data are necessary. The required capacity now is estimated based on the evaporator capacity. If we calculate, then 530 TR evaporator capacity is estimated. Uh, Evaporator capacity is divided into 2 parts, 265 TR each, because 265 on one side, 265 on the other side. The refrigeration capacity 265 on one side. One side means this is, we can say this is one side and this is other side. So 265 TR this side, 265 TR this side. And out of that also, uh, 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 that 265 Ti is further divided because into 2 systems. One for system, because in each side one system is for pre-cooling and other for remaining load, that is regular holding up load. Thus around 100 TR for pre-cooling and 165 TR for respiration heat and other internal loads, that is lighting load, motor heat, then transmission load, infiltration load, occupancy load, etc. Thus 4 independent systems, uh, 2 on either side of passage, are to be installed with common cooling tower for 2 systems as shown in the process diagram. Process diagram we are going to see. Now we have selected the 4 refrigeration systems to each side. 2 systems for holding capacity and 2 systems for pre-cooling capacity. The design saturation temperature first, that is -5 degrees Celsius, because for selection of compressor, we must know what should be the design evaporating temperature and uh, this things, condensing temperature. Sorry, this is a printing mistake. So design saturation discharge temperature, or we can say the condensing temperature. This is suction temperature, be evaporating temperature. That is -5 degrees Celsius and 40 degrees Celsius. So compressor models are selected again on the similar basis from the compressor catalog. So Witzer compressors are used, and these are the models selected. You can these model charts will be uploaded on the submission tab there. You can download the chart. You need to attach this chart as well. So how these are selected, you can check because here it is not visible. But based on the similar criteria, that is temperature conditions are given, -5 degrees Celsius evaporating temperature, and the cooling capacity. So where it meets, that model are selected. That model is selected. So the two, again, the like evaporator 2 models are selected. And this is a water-cooled semi-hermetical sealed uh, screw compressors. So these are the specifications of these 2 compressors. So one compressor of having 80 TR capacity and one compressor having 61 TR capacity. So accordingly, to meet the requirement. So ATTR 6 units, one becomes a standby because on one side there is a 260 for 165 TR. So 165 is the holding capacity. So ATTR compressor will meet two ATTR compressors on one side and one standby. So three on one side, so total six. And here the capacity is around 100 TR, but slightly 100 means 100 TR or 50 TR compressors are not available. So 60 TR two compressors we can use to meet 100 TR, and partly this load is also shared. So 60 TR. So again, 60 TR means 60 TR two on either side. So four compressor and two standby each. So two standby units are used, four are running, and these are the specifications you can see, and these are the models selected. You can cross check from the catalog also how these models are selected. So judicious selections of the models is also important because major criteria is your temperature limits -5 degrees Celsius, 40 degrees Celsius, then your cooling capacities. And that cooling capacity is further divided into multiple units. So 165 TR means 80 to 90 TR capacity is required. So that capacity is chosen. So 80 TR is our capacity, and here 100 TR, but 50 TR compressors are not available. So 60 TR. So this way the compressors are selected. The two systems we can see 61 TR capacity each for pre-cooling process, designed with 50% standby, and so every system one unit is standby. Because in case of breakdown, or also it is recommended to run the compressor alternately 8 hours duty we can alternately assign for the compressor, because one particular compressor cannot be, it is not recommended to run more than 16 hours. So every 8 hours if we change means one particular compressor can maximum it can run up to 16 hours. So accordingly 50% standby is there, means for 160 TR, the 80 TR standby, that is 50% we can say, or for suppose 120 TR, 60 TR standby. So like that, the compressors are selected. Uh, Condensers, again, to meet the requirement, it is necessary to have the following information for condensers. So now already the total refrigeration capacity known to us, evaporating temperature, condensing temperature, water temperature available. So these are the information required. Out temperature, what should be the delta T across or the water temperature drop requirement, that is generally 5 degrees Celsius it is assumed. And based on that, the shell and tube condensers models are selected. Again, models are selected based on the same how to go for 2-pass, 4-pass. So obviously 4-pass gives more delta T. So 4-pass models are selected. These are the two models are selected. And the capacity, this is our range, that is with 30 degrees Celsius. So these models meet the requirement, that is 130. So we can see these are the models selected. So 130 TR, two models, and 170 TR, two models. So 170 because 160 TR is the cooling capacity of one side for holding for regular load. So to meet that, 171 means slightly oversized condenser is selected, one on each side. Similarly, this is for pre-cooling application. So two separate condensers are used. Now, in order to achieve this 5 degrees Celsius temperature rise, the gallon required is also obtained from the chart. This is actually a recommended flow rate per gallon per TR. Again, this is from the chart it is selected. I will attach that chart and how we can select this chart. So the total that is 390 for model 1, that is gallon per minute, and 513 for model 2 for actually that is the total mass flow rate required. So accordingly, this information is required for selection of pump, condenser pump. So these are the various information, that is if what are the number of passes. Number of passes are more because Here we can get a greater delta T because 5 degrees Celsius is there. That's why number of passes, but it leads to increase the pressure drop as well. But obviously the condenser size is reduced considerably. This is condenser model. We can see shell and tube condenser model. This is water in, water out, and shell in, shell out is the refrigerant. You know, then expansion wall. Obviously, it mainly depends on the pressure difference between evaporator uh, and condenser. The following data is required. So evaporator temperature, system capacity, pressure difference across the wall. These are the information. In general, the first two factors determine the required flow rate through the walls. What should be the size required, that is capacity or evaporating temperature, where the third determines the size of opening required. So opening reduces the pressure, increases the pressure drop to deliver the desired flow rate. The flow rate is proportional to the pressure difference across the orifice. This is about the expansion wall. Cooling tower, to select proper tower from the rating table, following data must be known. So the desired tower capacities, our compressor capacity, total capacity is 280 TR on one side, because 160 plus 120, so around 262. So the one side, the capacity requirement is 280 capacity cooling tower is required. Then the design WBT, again based on the geographical area, what should be the WBT there. So this is comparatively for humid climate 27 degrees Celsius. Condensing entering temperature available, and what is the total water flow required. So these are the information required for selection of cooling tower. So this model, because 280 model is available, 2 units are required, and it meets the gallon as well because 903 here slightly oversize is used. And it is again, this is atmospheric condenser where no fans are used, only with the help of atmospheric air we can achieve cooling. So here the energy saving takes place because this is especially because it is placed in atmosphere, and the cold storages are generally installed at the remote places away from the urban area. So space is not that much the major criteria, because if the space constraint is there, then the forced cooling towers are generally used, but and they are generally installed at the terrace. But if the space is more, because atmospheric cooling tower require more space, but it consumes less energy because no fans are provided here. So this is atmospheric condition, and this is selected from again from the chart. Again, on the similar basis, we can select, this is 280, means the selection is around 4 gallon per ton, and based on this tower basin temperature is around 78, and 4 gallon per ton is selected because that meets the requirement of 1100. So instead of so slightly higher capacity. So here the meeting capacity is 280 TR, it comes here. So this model is selected, only one model. So this is a process diagram for onion cold storage. So all the equipments, these are the evaporators installed. So 2 each units. So here the capacities are slightly different. So 4 units are there. So this side is for holding capacity, or this entire system is there for cooling capacity. That is a regular cooling capacity. And this entire system is for the pre-cooling. So the two systems are used, and identical systems are used on either side. But for this particular side, single cooling tower is used. Here also single cooling tower is used. We can see the actual refrigeration load is 512 TR, but evaporator capacity is chosen is slightly oversized, that is 523 for safer side. Even compressor capacity is slightly greater than evaporator capacity, but the condenser capacity is even greater than the compressor capacities. So there is a proper balance, a slight, because based on the availability of the equipment, there must be a slight variation between the capacities, but it should be in the increasing order, because the condenser capacity must be maximum. It should meet the maximum requirements, because here the more area is provided, so it that even in some cases, even in the water temperature increases, the surface area will compensate the condensing temperature. So here this ensures the complete capacity balances of all equipments like evaporator, compressor, condenser, and cooling tower. And even all three capacities are greater than the required refrigeration capacity. So obviously, slight over size capacities, because this is bound to happen, because exact capacity equipments cannot be available sometimes. So that's why close to that, but it should be greater than the maximum capacity. So it is selected. So this is a refrigeration system. If we explain one particular refrigeration system, so from the compressor, this black line is insulated line. So this is coming from the evaporator. So this low pressure, low temperature evaporator then comes to the compressor, compresses to a required pressure. Then the red line, these are generally color coding, such color codings is used. Insulation lines are generally black insulations, so that's why black color is used. Then it compresses, then red color is used for discharge line. So the common discharge line, then it goes to the condenser. So after condensation, the yellow color is used for the liquid line. So proper shut-off wall is also used to stop the supply. Then this goes to respective evaporators, and every evaporator has a expansion valve immediately at the entry of the evaporator. So this way the cycle is completed. Then this is evaporation, then this is suction line, then compression, this is discharge line, then condensation, this is liquid line, back to the evaporator. So similar circuit is there for pre-cooling. We can say this is evaporation. After evaporation, it goes to the compressor, then compression, then discharge line goes to the uh, uh, condenser. From condenser back to the evaporator. So these are the pipings provided, and the separate systems are used. Means in case of suppose if there is no pre-cooling, then we can shut down the entire system, so without affecting the regular load. So these are the regular systems, and these are similar replica is there on the other side. And to meet the requirement, this is condenser, and the cooling water circulating in the condenser, which takes up heat from the refrigerant. It again pumped to the this line. This is again pumped over the cooling tower. Then it reject it to the atmosphere, and from the cooling tower back to the condenser. So this is a cooling water line. So this is cooling water. This is for one. This is second. So the incoming cooling water, outgoing cooling water when it after taking the heat of refrigerant. So this line and this is a common line is also attached. So for example, this is and this common line is connected here. So slightly, this is the line. Okay. So this is the process diagram for onion cold storage. It's a completely designed. All the components are selected. Their arrangement of the equipment, arrangement of the piping that we have discussed. Mm, And finally, we can write the conclusion. This is the maximum capacity. The plant refrigeration plant layout is developed in such a way that the transmission load should be minimum. All the equipment should be close to each other. So minimum piping, that is a piping design, role of piping design. So refrigerant has to travel a minimum distance so that the pressure drop will be reduced, and consequently the compressor work will reduce. The total load is divided into 6 chambers. So uniform distribution, that will make sure in case of or that will uh, adjust the load during the low demand case. Means accommodation of almost 1/6 capacity, we can run the system. So better flexibility is there. So the mechanical room is opposite to the entry side to minimize the intervals. So obviously, because for entry region is totally on the opposite side, so that will help us for loading and unloading. R22 vapor compression system is designed to meet the required refrigeration load, and the shut-off valves are used in the system to accommodate the load flexibility of the system. In between, the shut-off valves are used, so we can disconnect any system from because there are four systems working. So if the plant capacity of is a 50, if the pre-cooling is not there, then we can shut off both pre-cooling systems. If suppose 50% pre-cooling is there, we can run only one system. And in that also the multiple compressors are used, 6 compressors are used. So we can, by doing the compressor modulation, we can reduce that capacity as well. The separate systems are used for pre-cooling and product holding processes. That is, these are the conclusions. In this particular experiment, you have to write as it is. Only you need to understand the experiment because that gives you greater experience of designing also. So obviously the content remains same, that problem statement same, you have to copy, design criteria same, you have to copy, refrigeration system selection procedure remains same. Same you have to copy, that is selection of refrigerant part, then plant equipment, process layout, you have to just attach the same sheet, and a conclusion part, that whatever. So you have to copy this experiment as it is, but appendix you have to attach all the selection tables of the equipment with marking. So only one thing you have to do, that how these models are selected. Accordingly, you have to highlight because the bare charts will be uploaded. So accordingly, you have to only highlight the selected model. So that part only you have to do. Uh, that is for understanding purpose why how the model of the refrigerants components are selected. So at the end of this particular session or this particular experiment, you will definitely learn how to select the refrigerant for any given application. Now, in this case, we have discussed cold storage. Then how to select a refrigerant equipment to meet the refrigeration load. That selection of equipment is also play important role because previous part we have estimated the refrigeration load. So to meet that load, how we can select evaporators, then a compressor, condenser, and cooling tower, that we have discussed in this particular session, that you come to know how to select these equipments and other criteria of the selection as well. Then how to develop efficient process layout and arrangement of equipments. So how the equipments are arranged, how the layout is done, the location of compressors, condensers, then cooling tower. Obviously, cooling tower is outside here. Then evaporators arrangements and the fitting all these pipings of it. That you can definitely learn from this particular session. So with this, we have completed this experiment number 3, but this experiment 3 is slightly a lengthy experiment, but it gives a greater experience for designing of cold storage. This is still a generic design process. Uh, More minute fields are there, but once you know this, these are the common basic steps of designing. Definitely, this particular experiment help you to design the actual cold storage as well. Because cold storage applications, as far as the India is concerned, India is the largest vegetable manufacturer companies or country, and it's second largest country where the fruits are produced. So obviously to use these fruits or vegetables for the entire year, because few fruits are seasonals, but still we can mm, these fruits are available for the entire year thanks to the cold storage. So cold storage application is vast, and if you get chance in working in any refrigeration companies, definitely some companies take the contract of installations. So this particular experiment will help you there. So preserve this experiment and understand this experiment, because as if you can even show as if this experiment you have, or this particular system you have designed at your home. So all these three experiments are very important during your interviews, especially RAC interviews, RAC companies interviews, because all these three experiments are the case study time. So I hope you will definitely understand from these sessions or these video sessions. Even though you don't understand, you can rewatch these videos for better understanding, or you can free to contact me anytime. Uh, with this, we have completed all the laboratory part as well, and looking forward for good outcome from this experiment from you. Thank you very much.